All right, class, welcome. We are now on to 10.5 independent and dependent events. So we kind of talked about compound events, right? Where that's multiple events at once. But now we are going to look at multiple events at once, but sometimes some events are going to change the outcome of other events. Sometimes they're not going to change the outcome of other events. So that's what we're looking at today. So first we need to understand the language. An independent event is when one event does not affect the outcome of another event. The two events are completely separate. For example, rolling a die and then flipping a coin. If you roll a two, you're not more likely to get heads. They have nothing to do with each other, right? Rolling a cube or drawing a card. Those are independent events. You draw another example. You draw a card and then you put the card back and you draw another card. Just because you drew a 10 first doesn't make it less likely that you're going to draw a 10 again, right? You have the same exact chance. Whereas a dependent event is when one event does affect the other. The big example is you draw a card. So say you have a deck of cards, you draw a card and then you throw it away, right? If you draw a jack and throw it away, the chance of you drawing another jack is a lot lower because there's only three jacks left, whereas every other card there's four. So when you chew it up and eat it or whatever and don't put it back, that's a dependent event. Whatever you drew, that means you're less likely to draw that again. So dependent events when one event does affect the other event. All right, so now we're just going to tell whether these events are independent or dependent. Teacher sends a student outside from a table, and then a teacher sends a student outside from another table. Are they independent or dependent? Well, they're independent. Why are they independent? Because just because I threw out that one kid from a table, that didn't have anything to do with that other table that was going on, right? So I threw that kid out, not because I threw that first kid out. It's not like I threw a boy out the first time. Oh, now I have to choose a girl to make it even. No, that kid was talking, so I sent him out. It didn't matter. The next one, we select a student to do a noontime activity, and then we select a student to be a backup person for the noontime activity. That's dependent. Why is that dependent? Because if I pick one person, that means I cannot pick that same person again, right? Since I can't pick that same person again, it's dependent. If I picked Charles the first time, well, since I can't pick Charles, that means Doug over there has more of a chance to get chosen now, right? He has a chance to be a backup, a better chance to be a backup than he did before. So those two events are dependent. Well, coins flip two times. The first time lands heads and the second time lands tails. That's independent. The reason it's independent, just because you landed heads doesn't make it more likely to land tails. The second time, you just happen to land tails, right? And then a jar contains three green and three red. You choose a marble and you don't replace it. So if you choose a red marble and put it away, and then you choose a green, that's dependent. The reason it's dependent is because since you drew that red marble, now there's two reds and three greens. You are more likely to choose a green marble. Whereas if you would have chosen a green marble first, there would have been two greens and three red. So you'd have had more likely to choose a red marble the second time, whereas the first time was a green. So that's dependent because it matters what you draw first. Whatever you do first, that affects the second outcome. That changes the percentage, the probability of getting that red marble or that green marble the second time. The formula for independent events is just separate. So the probability of flipping a coin and rolling a die of what you want, you just find the two probabilities separate and then multiply them together and you get your answer. For example, if you have a die numbered 1 through 6 and a deck of cards labeled A through J, that's going to be A, B, C, D, E, F, G, H, I, J. That's 10. And we want to know the probability of rolling a 3 and a card with the letter E. Well, you first find the probability of rolling a 3. The probability of rolling a 3 is just 1 over 6. You have 6 options, 1, 2, 3, 4, 5, 6, and there's only one number 3. So remember, it's not 3 out of 6, it's 1 out of 6, right? And the probability of getting an E, well, there's 10 letters, and the probability of picking the one letter E is 1 out of 10. So we found 1 out of 6, we found 1 out of 10. Multiply those together, you have a 1 in 60 chance of getting a 3 and the letter E. That's not very good odds. 1 out of 60 chance. All right, two dependent events. This formula looks weird. You find the two probabilities separate and multiply them together again, but the probability of that second one depends on the first one. So you must first find the probability of that first event and then find the second one based on the first one. And we're going to do an example. An ice chest contains 5 cans of Sprite and 6 cans of Coke. Without replacing, what's the probability of randomly choosing a can of Sprite and then randomly choosing a can of Coke? So first, randomly choosing a Sprite. Well, there are 6 Sprites, right? Or there's 5 Sprites. So there's 5 Sprites and there's 6 Cokes, so there's 11 total. So you have a 5 in 11 chance of grabbing a Sprite. But now, say you grab the Sprite. So now there's not 11 cans left, right? There's 10 cans left. But how many Cokes are there? There are 6 cans of Coke and there's 10 total. So 6 out of 10. 1 can is already gone. So therefore, there are only 10 cans left. So you multiply that and you get 30 out of 110, which simplifies to 3 out of 11. So your probability of grabbing a Sprite and then a Coke is 3 out of 11. Notice, we only got that 6 out of 10 because we grabbed a Sprite first. If we would have grabbed a Coke first, we would not have 6 out of 10 anymore. There would only be 5 Cokes left out of 10, right? So that's why it's dependent, because it matters what you grab first. Do some more examples. An ice chest contains 5 cans of Sprite and 6 cans of Coke. We're doing that again. Without replacing, what's the probability of grabbing 2 cans of Sprite? So remember, the 1 can of Sprite was 5 out of 11. But now we grabbed the Sprite. So there's not 11 cans left, there's 10 cans left. And there's not 5 cans of Sprite left, there's 4 cans of Sprite left. So 4 is because we already took 1 Sprite away. And the 10 is because we took 1 Sprite away also, right? Where's 1 can missing from the chest? So you multiply these together, you get 20 out of 110. Cancel out those zeros, guys, and you get 2 out of 11 as your answer. So now let's do 2 cans of Coke. So to get a can of Coke first, you have a 6 out of 11 chance, right? But then we took 1 can of Coke, so now we have 5 cans of Coke left. And since we took 1 can out of the ice chest, we only have 10 cans left. So that's going to be 5 out of 10. So you multiply those together and you get 30 out of 110, which is 3 out of 11. So you have the same probability of getting 2 Cokes as you do of getting 1 can of Sprite and then 1 can of Coke. They are both 6 out of 11 times 5 out of 10. Next one. You flip a coin 4 times. What is the probability of showing tails all 4 times? Well, guys, this is independent. It doesn't matter what I flip first. It doesn't affect the new flip. So the probability would be probability of getting tails, probability of getting tails, tails, tails. Well, the probability of getting tails is you have a 1 in 2 chance, right? You can get heads or tails. So you have a 1/2 chance. But then it's 1/2 times 1/2 times 1/2 times 1/2 because all the probabilities are separate. They don't affect one another, so they're all 1/2. Multiply that together, you have a 1 in 16 chance of getting tails 4 times in a row. That's not very high. A jar contains 2 white chips, 3 blue chips, and 5 red chips. Without replacing, what is the probability of drawing 3 red chips? Guys, I know this is dependent because it says without replacing. Whenever it says without replacing, that is automatically going to be dependent because is affected by the previous probability. So first, how many chips are there total? 2 plus 3 is 5, 5 plus 5 is 10. So there's 10 chips total, and we want to find the probability of getting 3 red chips. So let's find the probability of getting a red chip first. 5 out of 10. Now, there's not 5 red chips left, there's 4 red chips left. And since we took a chip out, there's now 9 chips. So that means we have a 4 in 9 chance after taking one out. Now we take another one out, that means we only have 3 red chips left, and there's 8 chips total. So 3 over 8. We multiply all of these together, and we get 60 over 720. We'll cancel out those zeros. We get 6 out of 72, and 6 times 12 is 72. So if we cancel the 6's out for both, we get 1 over 12. All right, guys, that's it for the lesson. If you were confused, go ahead and rewind it and watch those videos multiple times. So it's page 433, 1 through 20 all. It's going to be due on Friday. All right, challengers, good job with this lesson. This is probably the hardest lesson So I hope you guys understand it and really get it. If not, go to office hours. All right. See you later, challengers. Peace.